Section 1. The Scourge of Grit. Protecting wastewater treatment from abrasive invaders. Wastewater, a complex mixture teeming with contaminants, presents a unique challenge for treatment facilities. Among these contaminants, grit stands out as a particularly troublesome foe. Composed of sand, gravel, and other abrasive particles, grit poses a significant threat to the smooth operation of wastewater treatment plants. Left unchecked, grit can wreak havoc on pumps and other mechanical equipment, leading to costly repairs and downtime. Furthermore, grit accumulation within treatment tanks reduces their effective volume, hindering the efficiency of subsequent treatment processes. The importance of effective grit removal, therefore, cannot be overstated. Section 2. Engineering the flow. Principles of efficient grit removal. Effective grit removal hinges on a simple principle: controlling the flow of wastewater to allow for the settlement of heavier grit particles while keeping lighter organic matter in suspension. This delicate balance is achieved through carefully designed grit chambers, the first line of defense in the wastewater treatment process. Grit chambers come in various shapes and sizes, each tailored to specific flow rates and grit characteristics. Factors such as the velocity of the wastewater, the detention time within the chamber, and the geometry of the basin all play crucial roles in determining the efficiency of grit removal. By carefully manipulating these parameters, engineers can optimize grit settling while minimizing the capture of organic matter. Section 3. Sizing up the challenge. Design parameters and calculations. Designing an effective grit removal system requires a thorough understanding of the incoming wastewater characteristics. In this case study, we consider a wastewater treatment plant handling a maximum flow rate of 61,502 cubic meters per day, with an influent biochemical oxygen demand of 494 milligrams per liter. BOD serves as an indicator of the organic content in the wastewater. To determine the appropriate dimensions of the grit chamber, we can employ the following equation, which relates the surface loading rate to the flow rate and surface area of the chamber. SLR equals Q divided by A, where SLR is the surface loading rate, typically in the range of 20 to 40 cubic meters per square meter per day. Q is the flow rate of 61,502 cubic meters per day, and A is the surface area of the grit chamber to be determined. By selecting a suitable SLR based on industry standards and the specific characteristics of the wastewater, we can calculate the required surface area of the grit chamber. The depth and other dimensions can then be determined based on hydraulic principles and design guidelines. Section 4. A case for clarity. Real-world application of a tailored grit removal system. To illustrate the practical application of these principles, let's examine a case study involving a municipal wastewater treatment plant facing challenges with grit accumulation. The plant, designed to handle a similar flow rate and BOD as our previous example, was experiencing excessive wear and tear on its pumps due to inadequate grit removal. Through a comprehensive assessment of the existing grit removal system and the characteristics of the incoming wastewater, engineers identified several areas for improvement. The existing grit chamber was undersized, resulting in high flow velocities and insufficient settling time. Moreover, the chamber lacked proper baffling, leading to uneven flow distribution and reduced grit capture efficiency. Section 5. Beyond the basics. Advanced technologies and optimization strategies. While conventional grit chambers provide a reliable method for removing larger, heavier grit particles, advancements in wastewater treatment technology have led to the development of more sophisticated grit removal systems. These advanced technologies, such as aerated grit chambers and vortex separators, offer enhanced performance and efficiency, particularly in handling finer grit particles. Aerated grit chambers introduce air into the wastewater flow, creating a spiral flow pattern that enhances grit separation. The injected air also helps to keep lighter organic matter in suspension, further improving the selectivity of the grit removal process. Vortex separators, on the other hand, utilize centrifugal force to separate grit from the wastewater stream. These compact and efficient systems are particularly well suited for handling high flow rates and variable grit loads. Section 6. A foundation for the future. Ensuring environmental sustainability through efficient design. In conclusion, The importance of efficient grit removal in wastewater treatment cannot be overstated. By protecting downstream equipment, enhancing treatment efficiency, and minimizing environmental impacts, well-designed grit removal systems serve as a cornerstone of sustainable wastewater management. As we continue to face the challenges of population growth and increasing water scarcity, the optimization of wastewater treatment processes, starting with effective grit removal, will play a critical role in ensuring the health of our planet for generations to come.